Today we're going to talk about Newton's universal gravitation. So we've got the formula and we got some of what the meanings of the stuff in the formula is. We're going to talk about this in a lot of detail as we go throughout this little slide, or sorry, these few slides. So Newton's universal gravitation, first of all, is the formula: force of gravity equals big G m1 m2 over r squared, where big G stands for 6.67 times 10 to the negative 11th. M is just a constant. It's always going to be the same. So this number right here will stay constant. And the M1 and M2 stand for the masses of the objects involved. And R is the distance between the centers of masses. So you want to go to the center of the masses. So for example, if you were a person standing on the surface of the earth, the distance would not be to the surface of the earth, but to the center of the earth. So that's what I'm demonstrating right here. By that same token, if there's a satellite orbiting something in space, you would not go to the surface of the objects. You would go to the centers of the objects. So the distance between the center of the earth and the center of the satellite would be that R, as opposed to just from here to here. This is not R. The distance is in between the centers. And then lastly, if you've got a person that is two people that are standing next to each other, the distance between them is the distance between their centers. And I tried to indicate that here. Okay. Now, to be honest, most of the time, if it's two people like this, we don't really care all that much about this measuring specifically between their centers. It's just kind of implied in the problem if they give you a number. Now, real quickly, why is this important? Well, this is important because all masses, regardless of what it is, all masses have a force of gravitational attraction given this formula. So any two masses in the universe are attracted using this formula that Newton developed. All right, and here's a little diagram to show you how this is set up. We've got the mass 1 and mass 2, and one thing you should notice is that the force is equal and opposite on the two forces. So in other words, if you're standing on the earth, not only is the earth pulling you down, but you are pulling the earth up, and those two forces are exactly the same. Okay. I should mention, just as a brief aside, that the force, Newton's universal gravitation, is a valid theory that works across most of the solar system. Most of the time when they send out stuff like probes into space, they're using this formula. Technically, it is not absolutely true because Einstein came along and overthrew it. And if you want to know more about what Einstein did, just Google Einstein and gravity, and that should give you a lot of stuff. It's a lot about curved space-time. There's some interesting stuff there, but you can do that research on your own. It's very important, but I would recommend, I don't want to go over it in here because it's not necessarily going to show up on the test. Okay, so Cavendish was a man that did an experiment to determine what G was. So G, if you'll remember, was 6.67 times 10 to the negative 11th, and Cavendish was proving what this actual number was, and he did it in like the 1700s. It was really, really early on. So the basic premise of what he did was he had a basic setup like this, where he had two small balls right here and two large balls right here. And what he did, and I think you can see this a little bit better from these other pictures, he had these small balls attached to a string, and that string had a mirror on it so that he could observe slight changes in direction. If he basically had a beam of light that was shining in here and hitting and then coming off. Well, if the strings spun, you would still have that initial beam coming in the same way, but now that other angle is going to change. And he could measure that angle and essentially measure how much force was provided by measuring the angle that was caused by bringing these larger masses in. And so what happened was he had these masses, the purple masses were outside first, and he had this thing just hanging, and he took a measurement. And then he brought these purple masses in near the green masses, and they were attracted. And since they were attracted, it changed the direction that mirror had, and it was actually able to change the angle. And essentially, by doing a lot of math, he was able to figure out what the universal gravitational constant was. Anyway, the reason I wanted to introduce this to you is there's a problem on the homework that shows this, so I just wanted to have a general idea of what this was. The problem on the homework essentially is just they tell you the weight required to readjust, and it is equal to the force of gravity between them. And that's the essence on that problem on what you need to do. Okay, so there are some problems that we have to do with this. The first one is the plug and chug method. And the plug and chug method is essentially just governed by plugging into the formula Fg equals big G m1 m2 over r squared. So for example, on this one right here, number 1, you would just do force of gravity equals 6.67 times 10 to the negative 11th times 80 times 50 divided by 5 squared. So you're just taking the masses and the distances and you're plugging them in. So if we did this, we did 6.67 second E at negative 11 times 80 times 50 divided by 5 squared, you would get 1.06 times 10 to the negative 8th newtons. Now you'll notice that's a really small number, and it's because the constant is incredibly small. So you need a really, really, really big mass to equal any kind of measurable force, which is why the Earth's mass gives us such a measurable force, because it's a really, really large object. Okay, so what is the gravitational force of attraction between the Earth and the Sun? Well, these numbers look a lot different, but you do it the same way. So you would do force of gravity equals 6.67 times 10 to the negative 11th times 6.02 times 10 to the 24th times 9 times 10 to the 31st divided by 1.49 times 10 to the 11th squared. Okay. Now, all you got to do is plug this in the calculator and it'll spit out an answer for you. So just be aware that when you have this stuff on the bottom, that square, you would need to write it in the calculator exactly as you see it here, because otherwise the square will get messed up. Also notice on these, I'm not going to tell you the answer to this one. If you really want to know, you can type it in the calculator. Also notice that I could feasibly tell you the force of attraction between two objects. Like I could tell you the force of attraction was 500 newtons, and then tell you that the masses were 50 and like 6 times 10 to the 24th, and then ask you to tell me what the distance was, right? Like that's a legal maneuver for me to do. So I could tell you that we had 50, we have 6 times 10 to the 24th for our two masses, and then I could ask you what the radius of that object was. You could just solve it. All you'd have to do is maneuver the r back over to the left side, bring the 500 over to the right side, and you could find what r was. All right, so that's an option. All right, these are the plug and chugs. You're just plugging in numbers and then moving on. I guess the what if is the next type. So these are usually characterized by a question, what if I do this, what will happen to this? And typically the only thing we're looking at is the force of gravity. We're looking at what happens to the force of gravity if we change something. So the way you do these is you always start off with 1 times 1 times 1 divided by 1 squared. Now each one of those is connected to G, M, M, or R. All right, and they're in the correct location. So if you have these two side by side, you should be able to figure out where to plug in the numbers. So number 3 says, what will happen to the magnitude of the force if one mass is quadrupled? So we start with 1 times 1 times 1 divided by 1 squared. And then what I'm going to do is I'm going to replace one of the masses with a 4 because it's 4 times greater. I'm going to replace that one with a 4. And so we would get 1 times 1 times 1, or sorry, 1 times 1 times 4 divided by 1 squared is 4 over 1, which is 4 times. And the answer to this would be the force is quadrupled, or the force is increased, quadrupled, or you could say increase by a factor of 4. All right. So for another one, what will happen to the magnitude of the force if the distance between the masses is increased by a factor of 2? 1 times 1 times 1 divided by 1 squared. Well, in this case, I'm changing the distance. So I'm increasing the distance by a factor of 2. So if I increase by a factor of 2, I am going to double it. So I'm going to change that to a 2. And I would get 1 over 4. And that's what happens to the force, which would be 1/4 the original, decreased by a factor of 4, something along those lines. Now, you can't have more complicated ones. So we always start off with the 1 times 1 times 1 divided by 1 squared still. But what happens to the magnitude of the force if one mass is tripled, the other mass is reduced by half, and the separation is 1/4 the original distance? So this time it would look like this. And you'd get 1.5 over 1 over 16, which would be 24, I think. Nope. Hang on one second. 1.5 divided by would be 24, yes. So 24 times. Now, notice I could have told you that the original force was a number. What if I said the original force is 200 newtons? So now, what would be the new force on each of these? Well, the new force on 3 would be 800. 200 times 4. The new force on 4 would be 50. 200 times 1/4. The new force on number 6 would be 200 times 24, which would be 48,000. It would be a big number, 4,800. Okay, so that would be the differences that you would see. So if you have an original force, if you actually have a number for the original force, you just take that original force number and multiply it by the multiple that you've got here on your answer. Okay, so these are the what ifs. All right, next up, we've got centripetal force equals force of gravity. All right, so if things are in orbit and you have a planet, maybe you have a satellite orbiting that planet like this, that orbit we can say is circular. Now, technically, it's elliptical, but we can say, make an estimation and say that it is circular. If we're saying that it's circular, then the centripetal force is the force pulling it towards the center of the object, and the thing that is providing that centripetal force is the force of gravity, which means that we can say that they're equal to each other. So if I can find the force of gravity, I can find the centripetal force. Or I can plug in my numbers, mv squared over r, for the centripetal force, and big G, m of the big object, m of the small object, divided by r squared. And notice now I can do all kinds of solutions. I can solve for the mass of the big object, I could find the mass of the small object, I could find the velocity, I could find the radius, I can do all kinds of stuff with this. This is going to be important. What this leads into also is that, let's see, we can also do, we can also take this, how do I move this? There we go. All right, I can also take this and put it here. And what we can do here is we can do the same thing with acceleration and the acceleration due to gravity. So remember that the acceleration, the centripetal acceleration is v squared over r. But to begin with, let's look at what centripetal force and the force of gravity equal. So if you'll remember, centripetal force is mac, and force of gravity could be described as mg, where g is the acceleration due to gravity. So notice that the m's can cancel here, and we can be left with acceleration, which is equal to g, the acceleration due to gravity, or v squared over r is equal to g. But if force of gravity is equal to mg, so mg is the force of gravity, and big G mm over r squared is the force of gravity. The first mass here, would be the small object, and this mass here would be the big object. But notice what happens to the mass of the small objects. They cancel, and so we can say that G is equal to big G m of the big object over r squared. So like if this was the Earth and a satellite, then you could say the acceleration of the satellite was equal to big G, the mass of the Earth, divided by r squared, which would come out looking like this. V squared over r equals big G m of the big object divided by r squared. And again, you can do all kinds of solutions with this. Knowing that the acceleration due to gravity is the centripetal force can lead you to can help you figure out some different problems. So this might be a good thing to know. All right, the last thing is the universal gravitation. So knowing what we know from that previous one, we can say, you can take, remember UG is equal to mgh. What you can do is you can plug in the potential energy formula and then plug in the formula for, remember S is standing for small, so the mass of the small object in the problem would be equal to big G, mass of the big object in the problem, divided by r squared times r. Because if it's an object that's orbiting somewhere above the Earth, the h is going to be replaced by that distance r. It's the same basic concept, that height above the Earth becomes the r above the Earth, and or the distance from the center of the Earth. And notice what happens here is the r's cancel, and you're left with UG is equal to big G, mass of the small object, mass of the big object, divided by r without the r squared. So the force of gravity is big G m1 m2 over r squared. Potential energy is just big G m over r. You just take the square out and you got potential energy. Okay, so that's a formula that might be nice to know. Now all these formulas are nice to know. It's one of those things that you just need to be able to rely on. Hey, I know there was a formula for that, and go find it. Right? You will need to know them for the test, but for right now, just recognizing that, hey, I know there's a formula for that, I can go find it. That's the important part. All right. Let's talk briefly about artificial gravity. So here we have a space station, and on this space station, we're going to say it's got a radius of 200 meters. How fast must it spin to mimic Earth's gravity? Well, if we want to mimic Earth's gravity, we need the acceleration to equal 9.8 meters per second squared, because that's the acceleration due to gravity on Earth. And so what we would do is we would set the centripetal acceleration equal to 9.8 meters per second squared. Or we could do v squared over 200 equals 9.8, and we can solve for v. So if I do this, I would get 9.8 times 200, which is 1960, and then square root that to get v. V would be equal to, second square root, second answer, v would be equal to 44.3 meters per second. So it would need to spin at 44.3 meters per second to mimic gravity. Now, to answer that second question, what would happen as you move toward the center? So if we're out here on the surface on the outside, right out here, anywhere out here, we would be experiencing 9.8 meters per second squared. But what if we took one of these little tubes toward the inside? What would happen as we move toward that center? What would happen to the way we perceived gravity? Well, as you move in, notice that the omega for this thing would be the same. So the number of the angles per second would be constant. So as you go in to the circle, this r is going to go down. This is going to stay the same, so our velocity has to go down. All right? So as you go in toward the middle, the velocity is going to decrease, and if the velocity decreases, then the acceleration would also decrease, and so you would feel lighter as you went in toward the center of the station because the velocity would be dropping. All right? It's an important little concept. All right, last one. Let's look at a centripetal force and force of gravity problem and how these relate to each other. So first of all, we've got a satellite. Let me give you a couple of knowns. So the radius of the Earth is 6.4 times 10 to the 6th meters. And the mass of the Earth is 6 times 10 to the 24th kilograms. All right. So if we have a satellite orbiting the Earth 3 radii above the center, it has a mass of 3,000 kilograms. what is the force of gravity? What is the centripetal force? How fast must it be orbiting? What is the acceleration due to gravity? What is the centripetal acceleration? So we're going to try to answer all these questions. So the first thing we need to do is draw it. So if I draw this, first of all, let me do a better job. All right, here's the satellite orbiting. Boop, 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 boop. Boop, 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 boop. Okay, the radius, the thing they gave us was right here, 3 radiuses of the Earth above the Earth. But you have to go to the center of the Earth because it's got to go to the center of the Earth to get the force of gravity correct. So really, our R is equal to 4 Earth radii, or our R is equal to 4 times 6.4 times 10 to the 6th. Now, our mass of the Earth would be 6 times 10 to the 24th, and our mass of the satellite would be 3,000. So I could plug this in to the force of gravity formula, which if you'll remember is force of gravity equals big G m1 m2 over r squared. And so the force of gravity formula would be force of gravity equals 6.67 times 10 to the negative 11th times 6 times 10 to the 24th times 3,000 divided by 6.4 times 10 to the 6th. And then you would have to square the whole thing. You got to square the 4 as well. So if I type this in, times 6 second e 24 times 3,000 divided by 4 times 6.4 second e 6 squared, I would get the force of gravity on the satellite is 1831 newtons. All right. Now, I can check this. Notice that if it was on Earth, the satellite would weigh 30,000 newtons. So it's 4 times farther away. So if I divide it by, it's 4 times farther away. So if we do 1 times 1 divided by 4 squared, we get 1 over 16. So if I divide 3,000 by 16, I should get the rough answer, which is 108 or 1,875. So it's roughly the same. So this is definitely the force of gravity. On this one, you got to remember this is exact, whereas if we're using the 1 times 1 times 1 divided by 4 squared or something, it's not quite exact because that's assuming 10, stuff like that. Okay, so we've got this perfect. This is also the centripetal force because it's the force pulling it in toward the center of the circle. All right. So let's take a look at how fast it must be orbiting. So what we're going to do for that one is we're going to set centripetal force equal to force of gravity. We've already found that. It's 1831. And then this is equal to mv squared over r. Now this m is the mass of the satellite, which is 3,000. So 3,000 v squared divided by 4 times 10 to the, 4 times 6.4 times 10 to the 6th. It's got to equal 1831. So I can multiply those up and find V. So that would be 4.69 times 10 to the 10th, 3,000 V squared. If you do that, you would get V squared equals that number, and then you square root it. And you would get V is equal to 3,952 meters per second. Okay, so that would be the velocity that it would have to orbit with. All right, for the last thing, what we're going to do is we're going to compare acceleration to the centripetal acceleration to the acceleration due to gravity. So this would be v squared over r, and this would be big G m over r squared. Okay, so if we plug these in, we would get 3,952 squared over 4 times, coming back up here to the r, 4 times 6.4 times 10 to the 6th. And if I solve that, I get 0.611 meters per second squared. And if I do it with this one, we'd get 6.67 times 10 to the negative 11th This mass would be the mass of the Earth, so that'd be 6 times 10 to the 24th divided by, again, that R, 4 times 10 to the, 4 times 6.4 times 10 to the 6th, but I would have to square the whole thing, and if I do that, I get, guess what, 0.611 meters per second squared, because again, these two should be equal to each other, and so you should see that both of them equate to the same thing. All right, so I know this was a little bit long, but hopefully it will help you solve some problems. Please feel free to send me a remind if you need anything else.